The time response of a system to any input can be divided into two contributions: the transient response and the steady state. So, for example, if we have the output of a system, the response of a system to certain input, for example, like this function y of t, this signal, is the result of adding up two different signals. One is like this, and this is y t of t plus another signal, which in this case is constant, and this is yss of t. So y of t is equal to yt of t plus yss of t. Y of t is the transient response, and ss of t is the steady state. The transient response has the property that when t goes to infinity, it tends to 0. It decays. The limit of that part of the output when t goes to infinity is 0. So as time goes by, it tends to vanish. The steady state is simply what is left, what remains when the time tends to infinity. Well, obviously, if the input u of t keeps changing, it is very hard to distinguish what is transient and what is steady, because the input itself is not steady. This is why the concept only really makes sense for standard inputs like the step or the ramp or a sine wave, a sinusoidal function. The step response of a system provides us with very valuable information about the transient response and the steady state. However, if we want to quantitatively assess the performance of a system under a step response, so that we can compare and rank different systems, we need to turn the graphical information that the response is giving to us into numerical variables or parameters describing each performance. Now, there are 4 fundamental parameters related to the transient response of a system to a step input. And here we're going to use this example of output y of t of a system to define those 4 parameters. Well, the first one is the overshoot. The overshoot, or the maximum peak MP of the system, which is just the maximum value that the output takes along its response, that is y max, which is located right here. This would be y max minus the value of the output in the steady state, which is this y double s, the final value of the output, over the value of the steady state itself. That is, this is a relation, a ratio between this amplitude, the amplitude of the peak, over this segment here. Sometimes it is expressed in terms of percentage. So with an overshoot of 100%, the peak would be doubling the final value of the response. Okay, the second parameter is called the peak time, TP, and it is just the time in which this maximum value is reached. So this time here is TP, the time in which the overshoot takes place, actually the first overshoot, which is the maximum. Okay, the third parameter is called the rise time, TR, and it's defined as the time it takes the system to go from certain low value to certain higher value. So for example, in this case, this is 10% of the final response. This is 10% of YSS, and this is 90% of YSS. So this interval here, this interval is defined, this is TR, the rise time, but in this case defined as from 10% to 90%. So we could have chosen some other interval. We could have decided to measure the rise time as the time it takes the system to go from zero, from the beginning of the response to its value, to its final value, to the first time the system crosses YSS, and then we would get this value for the rise time, and in that case we would be talking about the rise time from 0% to 100%. Now obviously this last way of understanding the rise time only makes sense for systems which actually have overshoot, because otherwise the system never reaches the 100% of YSS. So you can see that by looking at the response of a system like this one. This response never really reaches YSS. It is approaching it, but it never does. So in that case, the R from 0 to 100% could not be found. Well, the rise time aims to give us a sense of the speed of a system, how fast the system responds. Okay, and finally, the last parameter is the settling time, which is denoted TS, and it can also be defined in different ways, or well, it has one definition, but like here with an implicit choice. The settling time is the time it takes the system to, or the output of the system, to enter certain bands around the well, I'll draw them with a solid line so that there's no oops. Let me try again. I'll draw a solid line around the final value, and these are error bands. Let's say they are plus minus lambda percent of YSS. Well, the settling time is the time it takes the system to enter the bands for the last time, which is the last time it enters, not to leave the bands ever again. So this is the last time that the system comes from from outside the bands inside the bands. As you see, the rest of the response remains within the bands. So this time here would be the settling time, TS. Now this is the settling time at lambda percent. So if we choose a higher lambda, then of course the settling time would be shorter. And as you see, the settling time for the other response I draw was this one. This is TS for this purple response. The settling time is telling us, in a way, when we consider that the transient response is over and the only response left is the steady state. So it's telling apart both ranges of the response. So these are the four parameters that we'll use to characterize the step response of any system, and the way in which many specifications, many transient specifications will be defined.